Okay, in this section I'm going to revisit polynomial and rational inequalities. What I'd like for you to do is just pause the video and read this highlighted section here, and after you read it, then you can restart the video and I'll take you through the steps here. So okay, so now let's say we wanted to solve a polynomial inequality that looked like this: x squared minus 3x is greater than or equal to 10. Well, the first thing you want to do is get all your terms on one side of the inequality. So let's write that as x squared minus 3x minus 10 is greater than or equal to 0. Then in order to find the values that you need, you're going to set that equal to 0. And what you're going to do is you're going to set that equal to 0, and when you set that equal to 0, if you can factor it, you want to factor it and then determine what the values of x will make this equal 0. And it turns out that x equal negative 2 and 5 make it 0. Now we can call those critical numbers, but basically you do a table where the table really just represents, your x-axis. So basically what we're looking at is a table that represents the, and so the critical numbers negative 2 and 5 break up the x-axis into 3 intervals: everything left of negative 2, everything between negative 2 and 5, and everything to the right of 5. Now the function can't change sign unless it crosses one of these critical numbers. So whatever the sign of the function is to the left of negative 2, it's going to have the same sign at every value to the left of negative 2. So I only have to test one value to the left of negative 2. So I'm going to test x equal negative 3. And now if I go back up here to this factored form, you can plug negative 3 in here, and you know that negative 3 plus 2 is negative, and negative 3 minus 5 is negative. So if you plug negative 3 into this expression, you're going to get a negative times a negative, which is positive. And then to test the middle interval, since 0 falls in there, I'm going to use 0. So if I plug 0 in up here, I'm going to get a positive times a negative, which is negative. So I get a negative there. And then if I plug a number to the right of 5, like 6 in, I'm going to get a positive times a positive, 8 times 1. So it's going to be a positive number. So the result's positive. Now I wanted to know when this expression x squared minus 3x minus 10 was greater than or equal to 0. Well, if you'll notice, the outer two intervals, you've got positive signs, which represents greater than 0. So I know it's greater than 0 for all values to the left of negative 2 and all values to the right of 5. And it equals zeros at those values. So the solution would be all values from negative infinity to negative 2, including negative 2, union 5 to infinity, including 5. So that's how we solve a polynomial inequality. Now here's one a little bit more complicated. You've got x cubed plus x squared minus 25x is less than 25. Notice this time I don't have the equal to with it. Now if I move the 25 across, I get 4 terms. Well, fortunately, if I set this equal to 0 and try to solve it, it does solve by factoring. I have to factor by grouping. So if I factor in x squared out of the first term and a minus 25, the first 2 terms, and a minus 25 out of the second 2 terms, I get x squared times x plus 1 minus 25 times x plus 1. And I can factor the x plus 1 out of there, and then I'm left with a factor of x squared minus 25. And then that x squared minus 25 factors into x plus 5, x minus 5, x plus 1. So here, if I solve that equation, I get 3 critical numbers: x equal negative 5, 5, and negative 1. So now I can break the line up into 4. So the 4 intervals are everything to the left of negative 5, everything between negative 5 and negative 1, everything from negative 1 to 5, and everything to the right of 5. So I can do my test values again. negative 6 in this interval, negative 2 in this interval, 0 falls in this interval, and 6 falls in this interval. And now go back to this factored form right here and plug in your test numbers. Now if you plug negative 6 in to those, each one of these factors are going to be negative, because you'll get negative 1, negative 11, negative 5. And negative times negative times negative is negative. So you're going to get a negative. Now if you plug negative 2 in, you're going to get a negative for the first, you're going to get positive for the first term, and then negative for the second two factors. So positive times negative is positive. And if you plug 0 in, you're going to get a positive times a positive, which is negative. And finally, if you plug 6 in, you're going to get positive for all three factors, so that product has to be positive. Now here we wanted to know, when is this polynomial less than 0? So to find when it's less than 0, I'm looking for the negatives. So negative infinity to negative 5 and negative 1 to 5. And notice here I didn't use brackets because it didn't ask when it equaled 0. I just wanted to know when it was less than 0. So those are the solutions. Okay, this one's a little tricky. X to the 6 is less than or equal to 64. We'll move your 64 over, and then this actually set this equal to 0, and it factors into, using difference of squares, x cubed minus 8, x cubed plus 8. But actually, if you go to your formula for difference of cubes, that factors into x minus 2 times this trinomial, and sum of cubes, x cubed plus 8, factors into x plus 2 times this trinomial. Well, it turns out that these two trinomials do not have any real solutions. So the only way that this product can be 0 is if x minus 2 is 0 or if x plus 2 is 0, which means x equal negative 2 or 2. So again, you can draw the x-axis there if you want, but negative 2 and 2 would be these numbers. And then so I've got three intervals, to the left of negative 2, between negative 2 and 2, and to the right of positive 2. So if I test these numbers, negative 3, 0, and 3, and I plug them into this form of the expression, then when I plug negative 3, I got a negative here, I got a positive here, I got a negative here, and I got a positive here. So I get a negative times positive times negative times positive. Well, since there's an even number of negative factors, it's got to be positive. When I plug 0 in, I got a negative here, a positive here, a positive here, and a positive here. So since I only have one negative, that product's got to be negative. And then when I plugged 3 in, all four factors gave me positive, and the product of positive factors is always positive. So I wanted to know when this expression was less than or equal to 0. Well, then that would just be this middle interval, because that's where I got the negative. But I also wanted to know when it was equal to 0, so I have to include the endpoints with brackets. So that's the solution. What's interesting is if you graphed this function here, where we got the solution was negative infinity to negative 2, 5 to infinity, well, remember, the question we asked was, when was this greater than or equal to 0? Well, look, it's equal to 0 at negative 2 because it crosses the x-axis, and it's greater than 0 to the left of negative 2 because it's above the x-axis. And then it's equal to 0 at 5, and then it's greater than 0 to the right of 5 because it's above the x-axis. And also this other one, you can look at it and see, well, we want to know when it was less than 0. Well, you can see it's less than 0 from here to here, and that would be as x goes from negative 1 to positive 5. But it's also less than 0 over here, so that would be from negative infinity to negative 5. So the solution negative infinity to negative 5 and negative 1 to 5 just correspond to the two pieces of the graph on the x-axis where the function is below the x-axis. And then this other one here, you can see that the graph it says when is this negative, and the answer was from negative 2 to 2, and you can easily see that from negative 2 to 2 the graph is below the x-axis. Now again, freeze the video and read this highlighted text, and then when you're ready, go back and we'll look at some problems. Okay, so this is a rational inequality. Let me move this to the other side, and then since they have the same denominator, you can actually rewrite it like this. Now, you're looking for two things here. You want to know when it's going to be 0, and it's going to be 0 when x minus 3 is 0 or x equal 3. And then you want to know x equal when it's undefined. It's going to be undefined at x equal -2. So those are both important areas to look for. Okay, I'm not going to spend a lot of time on this one, but basically the two critical numbers, break it up into 3 intervals: -infinity to -2, -2 to 3, and 3 to infinity. So pick a test number in each interval, -3, 0, and 4, and plug it back in to this expression, because you want to know when this expression is positive. So when I did that, the quotients I got were positive here, negative here, and positive here. So it's actually positive in the outer regions, -infinity to -2, and 3 to infinity. And it also said when did it equal 0. Now this is important. Notice I included the 3 with the bracket, because at 3 this fraction does equal 0. But I didn't include the -2, because at -2 this fraction doesn't equal 0. It's undefined. So don't include the -2. Alright, this one here is a little trickier, but let's move the 2 across first, so we get this. And then I want to get a common denominator. So if I multiply 2 by x plus 2 over x plus 2, that'll give me the same denominator. And then distribute the 2 through. Well, actually, I'm going to distribute the -2 through, and that's -2x minus 4. But now that I have a common denominator, I can combine these two and say x plus 1 minus 2 minus 4 over x plus 2 is less than or equal to 0, which finally gives me -x minus 3 on top, and x plus 2 equals 0. And from there we do it just like we did the last one. Find out what makes -x minus 3 equals 0, and it turns out that would be -3. And find out what makes this is undefined, and that's going to be -2. And then draw your numbered line, and you've got -3 as your first number, and then -2 is your next one. And then pick test points in each interval, and plug those test points back in up here into this expression, and see what sign you get. So here I got a negative, here I got a positive, and here I got a negative. And I wanted to know when this expression was negative or 0. So I'm using the outermost regions, -infinity to -3 and -2 to infinity. And again, don't include the -2, because that's where the function is undefined. That's not where the function is equal to 0. Okay, one more. Okay, so this one, if you factor it, you get this, and so it's going to equal 0 at -1 and 1, and if you factor the bottom, it's going to be undefined at 0 and 5. So those 4 numbers divided the number line into 4 regions, which you can see here, and 5 regions actually, and pick a test point in each region, like -2, and plug it into this expression, and I got positive. Plug -0.5 in from this region, I got negative. Plug +0.5 in, I got positive. Plug 2 in, I got negative. And plug 6 in, and I got a positive. Now notice that I wanted to know when this expression was greater than 0. So I choose the regions that gave me the positive: -infinity, -1, 0 to 1, and 5 to infinity. And you can view the graph there, and you can see that on those intervals the graph is above the x-axis. Now I'm going to leave you with this word problem and let you freeze the video and look at it. But basically all I want to do on this problem is try to find out when this expression is greater than 190. And then so if you subtract 190 across, you just want to know when this expression is greater than 0. So get your critical numbers, and you get 2 values, 0 and 6. And then so you just want to find the solution of that. Bye-bye.